Hi, everyone. Tom Immel here at UC Berkeley. I'm here to talk today about the ICON mission, give a progress report, and talk about our data products that will be discussed this week at the conference. I will share my slides, possibly. I have a number of co-authors. The whole science team for ICON, they'll become evident as I go through their products. ICON was launched in October of last year, and we entered phase E in December 1st of 2019. We had a good launch, fantastic launch, circular orbit out of Florida at 27-degree inclination, 575 kilometers, a little higher altitudes. The observatory's in science mode. It has been since then, and status is green. We did get a safe mode switch mid to late February, which we recovered in a few days. We're better at that now, so if we ever get a safe mode again, we'll be right back. That's the plan. Science payload's in great shape. The 4 instruments are highlighted here in bullets: MIghty, EUV, FUV, and IBM. They're all working great. You'll hear more about their products shortly. You'll see for yourself. We have high throughput remote sensing instruments and a fantastic drift meter and retarding potential analyzer working together to give us the parameters of the local plasma environment at the spacecraft. Mission ops, science ops, and science data center are all at UC Berkeley. That's come together rather well, and the ground station we've got there is a big part of our collecting the data, which 3 to 4 contacts per day come through Berkeley with several other stations around the world backfilling, giving us our full data downlink. Operations includes the calibration maneuvers, any science maneuvers, safing of the UV instruments, and planning all that, and uploading the commands to do all that on a weekly basis, and that comes from Berkeley. And the Science Data Center has all the software for the mission for levels 0, 1, 2, and 4 of the products. I will talk today about the level 2 products and give you some quick look at our first results. There's more to discuss at the science during this meeting at the ICON Data Product Workshop, and you can ask questions there live with everyone in attendance, which will include all the data product owners. I am going to march right through the data products. I have 15 minutes, so I'm highlighting the paper that discusses the algorithm. This one's by Brian Harding. The wind algorithms were developed by Brian and company. See on the author list. The principle of the retrieval is that the MIghty instrument is measuring the Doppler shift of red and green emissions of atomic oxygen. That retrieval is a fairly involved process, but once you're done doing the retrieval from the interferograms, you get down to a line of sight wind measurement for the 2 different views of the MIghty instrument, and those can be combined. The line of sight measurements can be combined to produce cardinal winds. That's the difference between the 2.1 and 2.2 product. The 2.2 is combined cardinal winds in magnetic and geographic coordinate references. This plot shows the wind measurements for one orbit, and we've got a lot of these. So the 2 boxes on the top are the red line emissions, the Doppler shifts from those used to retrieve these winds, and the winds in the bottom box come from the green line. We do have some overlap, which I'll mention, but first I'll draw your eye to the upper left-hand corner, which are the zonal winds, the east-west wind observed by MIghty during this orbit. And you see that noon is at the center, and that we have a full picture of the westward winds in the westward zonal winds in this region on this day. And of course, this, at nighttime, we have somewhat less signal below about 200 kilometers, but we still get good F region winds continuously at around 250. And that's looking very good. And you can compare it to a empirical wind model. The HWM14 model shows what you might have expected to see from MIGHTY. I think there's quite a bit more in MIGHTY to look at compared to the model, and we can talk, you can see for yourself when you go download these data. The right-hand plot is the same, but these are the north-south winds, the meridional winds. So we have a excellent wind product there with a lot of structures in those winds that are now available to the community. The green line winds are lower altitudes. Sorry, I should have highlighted these are 300 to 200 kilometers is this particular range. We go down below, and these features that you can see in the red line are reflected in the green line emissions or green line winds at lower altitudes, which are now here in the daytime extend from 200 kilometers down to about 90. At nighttime, the air glow emissions are much more limited, or their emission brightnesses are so low that we can only really work near the boundary of space and down in the mesosphere from 90 kilometers up to about 110. So, but we provide those winds continuously around for every orbit. There's particular nuance is that the daytime integration times are 30 seconds and the night times are 60 seconds. In any case, one feature you can see obviously in the green line winds are pretty remarkable features, particularly in the meridional winds in this case, with strong shears in the daytime, which are pretty stand out quite a bit in the data all the time. So I think this will be a great resource. Michael Stevens at NRL was in charge of the temperature retrievals from the MIGHTY instrument. The MIGHTY instrument uses a different technique to retrieve the temperatures by a photometric technique with altitude resolution, looking at different parts of the O2 A band. That A band changes in nature, its profile changes as a function of temperature, and by observing at different wavelengths, you can retrieve temperature pretty high precision. So there's just some examples here. I'll show you some actual examples. This is from a summary plot that from a particular orbit, also in January of this year, where you see one orbit to the next. A lot of structure in the temperatures. We're reporting temperatures down to 90 kilometers and up above 110 at this point. We are working to get that a little higher and to get both MIGHTY A and MIGHTY B reporting over the entire altitude range. But right now we have concomitant measurements from A and B that really match up well throughout the orbit. And this plot just simply shows some of altitude profiles of the temperatures compared to the red line, which is MSIS. Thermospheric composition is work that was led by Andy Steffen. We've benefited a lot from a lot of great input and analysis by Bob Meyer, who's at working with Scott England at Virginia Tech. That is coming out very well, but the idea is that with the FUV observations in the daytime, you can, and the emission rates that are predicted here, which turns out look quite a bit like what we went out and measured, you can, through a retrieval process, get to the N2 and oxygen altitude profiles as well. Given the shape of those profiles and given the fact that we're using MSIS to approach a solution that fits these data, you get to O2 and an exospheric temperature as well. That is work that is close to completion. We are currently only reporting the disk product, which is a line of sight measurement where it's a column, you're looking at a column integrated measurement of LBH and 1356 emissions of nitrogen and oxygen respectively, and getting you to a similar, what the product we actually want, which is the ratio of oxygen to nitrogen in the column. So this is an example. Again, we're back to the start of the year. We have these data available now up to June and back before the start of the year. So these show, a remarkably good product for understanding the changes in the thermosphere over time, day to day, week to week, and seasonal. So one thing to note is that we are off in the region of this South Atlantic anomaly, which is high radiation environment. This is the feature of the planet that you really have difficulty doing any scientific work in this region. The MIGHTY instrument has the same problem, and the EUV as well. We just turn EUV and FUV off. There's just too much radiation to work. Outside of that region, we're getting good column O to N2. We are planning to update soon to get the entire limb product out as well, as long as those disk measurements more or less match up with the limb measurements. You'll skip the movie. Oh, gee, well, you can see some of the data coming together in the movie. This is a daytime. You're not getting the nighttime. We're skipping the nighttime data. There are no nighttime data for O to N2, and you see how the data are built up over a day. The FUV instrument also observes nighttime emissions, and we can, from those emissions, this paper by Farzad Kamalabadi at Illinois and the others working with him on this product showed that this paper describes the algorithm by which you retrieve the nighttime O+ densities from the same FUV instrument, this time only using the 1356 channel of the instrument. You'll note that these brightnesses that we're expecting are pretty low. We were working towards a worst case solar minimum, and sort of had this, I think, looking at densities at midnight. Sure enough, it's very deep in solar minimum, and we have very faint emissions in the nighttime, from which we are able to do rather good retrievals that meet our requirements for precision. This next slide just shows some of that. These are particular a set of observations from a nighttime pass, where we're able to retrieve a number density profile from which you can talk about an NMF2 and HMF2, the sort of simple parameters by which we discuss the ionospheric densities. But we do have the entire profile for these nighttime passes as well. Next on the list of retrievals is the daytime O+ retrieval. In the extreme ultraviolet, this work also was led by Andy Steffen, and working closely with the instrument team at Berkeley really has put together a remarkable retrieval product that has given us very solid set of measurements for the O+ concentrations in the daytime. The nuance of this retrieval is that it's fairly involved, and it benefits from a particularly, this is a new capability we built into this instrument, which was to look at two different emissions in the O+. The 834 line is very bright in the daytime. It's illuminated, though, from the Earth. The albedo of the Earth is more than 1 at this wavelength. Most of the 834 that's coming from the Earth is created in Earth, and is created at fairly low altitudes, down near the photoelectron peak below 200 kilometers. The 617 emission is a more direct measurement of that. The 834 is readily scattered by the O plus in the ionosphere, and that's why you actually see this profile, because the ionosphere is scattering that emission as it's produced in the lower thermosphere. 617 is a better measure of what that emission profile actually looks like. And so I'm going to spend a little time showing off the output of that instrument. And I think it's beautiful. So there's a few features here. This is a limb view. So you can imagine that the Earth is brighter below you, and as you look up above on the limb, you get away from the bright Earth. But there's a couple bright features here. One is the 834 emission on the right-hand side. This is a 617 line we're interested in. In fact, I'll get to this in a minute. It highlights these emissions. This is a contaminating line, helium 584 line, which has a huge component coming from the interplanetary environment. This is a very readily scattered helium line that is abundant. There's an abundance of helium in our near Earth and solar system that scatters this light from the sun very readily. So our requirement was to see it. We want to make sure that it's not getting into our 617, and we feel that I think we met our goal of separating those two lines. So we get a hold of 617. It helps us infer the O plus densities by measurements of 834. This is just if you turn the whole instrument straight down and look at noon at the Earth, this is what the Earth looks like in those emissions. This is a calibration image. It allows us to understand the shape of the lines as a function of altitude when we turn it back to the limb. Compared to SDO, we're seeing the solar spectrum on the moon. That's pretty remarkable. The moon is a calibration target for us, and it's going to be a paper. And these are some of the O plus retrievals in the daytime. Again, we have a little gap over the South Atlantic. Other than that, we have a very good picture of the conditions in the ionosphere, showing HMF2 and NMF2 in these plots for a day. Last but not least is the data products supported by UT Dallas and a build of their heritage drift meter and retarding potential analyzer. It's probably, I think they'll say that it's one of the best ones they've ever built, and we're glad to be flying two of them. One, the flight spare is pointed in the aft direction in case we ever need to turn the spacecraft around. If there's ever a problem with IVM-A, IVM-B is waiting for us to turn the spacecraft around and put it in RAM. The principle of operation is that we're carrying a retarding potential analyzer and a drift meter. The simple principle of these instruments is pulled from this paper and shown here. That capability gives us a very good view of the ionosphere from one day to the next and how it's changing. There's just a lot of features in every single day of this the IVM data that we are interested in comparing to the dynamical environment measured by MIGHTY and the conductivity environment that's provided also by the O plus measurements in day and night from the EUV and FUV instruments. And of course, the thermosphere under disturbed conditions will affect the ionosphere as well. And we've already seen some of those cases, some of even the weak storms we've seen, I think in April. I will go on to show off a little bit more the comparison of the IVM with their wind measurements. Here's another highlight. I showed one orbit of the wind observations with the red and the green line. I'm showing you here a green line, successive green line passes, showing you sort of tantalizing results. There's a lot of features in the daytime thermosphere that are indicative of wave structures, shear layers, migrating effects, standing effects. There's a lot to talk about. So we're very pleased to be able to share these data finally with the community. You know, we built ICON and we flew it at these latitudes so we could do this. We can make wind measurements that are magnetically relevant or connected, if you will, to the drift meter measurements. So Brian Harding, with these advanced Python tools that people have their hands on these days, did a really nice job showing these data off and showing the drift meter observations of the vertical drift of the plasma. You can say, perpendicular to the local magnetic meridian motion of the plasma, and comparing that to the wind observations. We get a lot of those. Every time you cross the equator, you can do this. And so we have a lot of data in this area, with 15, 16 crossings of the equator in the daytime. You'd like to say, the precession of the orbit, sometimes these data are coming from the terminators, and there's a lot going on at the terminators. Not only we're switching modes on the mighty instrument for one, but most of the time during the day we get fantastic view of this region and this connection all the time for analysis. This just shows one of those conjunctions where we're looking now at the Hall-weighted winds and the Pedersen-weighted meridional wind and the Hall-weighted zonal wind, and comparing that to what's going on at the drift meter. And what's the story? That's there's to be continued. There's a lot of different processes in play, and the data are being analyzed right now. But of course, they're available to you as well. So we have a number of different conjunctions, different passes. As I said, we have hundreds of them. There's another thing you can do with ICON, which is do a conjugate maneuver. One of the questions you might have if you're looking at the northern foot point is what's going on at the southern foot point with the winds. We can rotate the spacecraft a couple times during an orbit, which this cartoon shows, where we put the lines of sight of the mighty instruments to the north and south of the orbit track. And we can then, if we do that again later, point to the same regions, but with A and B and then B and A, you get this line of sight winds that you can then again do as you did with the 2.2 product and get to cardinal winds in those brief moments where you're crossing the equator when the declination and the inclination of the orbit match up. So, and we can do that sometimes in 2 orbits in a row, and it gives us sort of really interesting data set to work with. We get to see the wind profiles in the north and the south and how they might differ. It's pretty remarkable case that the northern foot point and the southern foot point here, the zonal meridional winds are quite different. And then you can do work to get to a wind-driven current that would be that those winds should drive given the conductivity profiles that are estimated for those regions. One orbit to the next, things change a lot. And so it's a remarkable environment to be, it's remarkable to finally have these data. So I am nearly done. I just wanted to say that I'm sorry that we can't all be together to talk about all this good stuff in person, but I know there's going to be a lot of presentations online. So we will all be trying and fighting to get to everyone's Zoom or other ways of communicating during this meeting. And sorry, this slide didn't look so great. The point is, what I wanted to point out is that we have a ICON data tutorial coming up this week. And there's a lot of other sections which we're going to try to make too, and possibly discuss or present ICON as the workshop, as best for the workshop that's going on. Point out that if you can remember icon.ssl.berkeley.edu, you can find everything. You can find all the papers that I highlighted in this talk. at that site. And you can also find all the data products at that site. So it's not so hard to find the data tab or the publications tab, but these are the specific links that get you to the right spot. There's a few features of our data products. I mean, the NetCDF, you can put a lot of information in there to support for any different particular variable. You can append a note in its attribute that is that should have everything about that variable in it. And we've worked to make sure that our NetCDFs are self-documenting. The output of all those self-documenting, well, I should say, if you ask for all of those documents in the data product to be printed out and shown to you, we have those PDFs online as well. You can go pull down the PDF that describes all the variables in every single data product and work with them or contact a ICON science team member to help you understand what you've got. So ICON is providing data to revolutionize our understanding of conditions in geospace. I think that's fair to say. Thermospheric wind retrievals of this precision have never been achieved ever. And I am surprised to see all the features in the daytime thermosphere that I did not dream were there. We can see changes in the plasma environment as well as in the thermospheric environment. So the winds versus the plasma, the composition versus the density, the temperatures versus the winds versus the ionospheres. We work to retrieve tides and other wave features in the system. We are making the measurements from 90 kilometers up to 300 kilometers, and as we think space weather and the solar conditions are going to start picking up, we've seen some interesting storms so far. Actually, some DST events have occurred, and we're seeing effects right now. So, and they're not small. They're obvious in our data that there's a storm going on. So very cool to see. All 7 data products are coming out this week in Science Data Center. The only caveat with those are that the OTA N2 is a disk product. It's a column integrated ratio of oxygen nitrogen. We are working on getting the LIM product verified and out. And we're also working on extending the altitude range of MIDI B so that it matches MIDI A. With that, I thank you for your attention, and I wish you all a very good meeting.